much.
You're welcome.
All right, let's get. So our next presentation is by Vivek at IIT Delhi. So I'll turn it over to Vivek.
Yes, thank you.
All right, we can see your screen. So if you make it full screen and go ahead.
Yeah.
Great.
Hi everyone, myself Vivek Narayan. I am a research scholar at IIT Delhi under the supervision of Professor Beam Singh. I am here to present a presentation on seamless mode control of microgrid for optimal coordination of conventional and renewable energy resources with improved power quality. I am working under US's project of theme for microgrid and active distribution system. These are the outlines of my presentation. Starting with a brief introduction, as we all know that the demand for energy is getting increasing day by day. Hence, therefore, energy crisis, and to improve the reliability, there is need to integrate various distributed resources at the point of common coupling. And nowadays, the common trend is towards renewable energy resources. As we can see from here, the solar as well as wind energy are getting more importance day by day. Hence, the importance of microgrid is coming into picture. A microgrid is a group of interconnected loads and distributed energy resources within clearly defined electrical boundaries that act as single controllable entity with respect to the grid. And the microgrid can connect and disconnect from the utility grid and can be operate in grid connected mode as well as islanded mode. And the basic needs of microgrid are microgrid could be the answer to our energy crisis as well as transmission losses can highly reduced and provide high quality and reliable energy supply to critical loads. The microgrid encourages to use renewable energy sources, hence can reduce the CO2 emissions. And the main objective is to optimize the usage of renewable energy source and to minimize the usage of conventional diesel generator source to feed the critical loads without causing any power intermittency, and to improve the quality of power injected to the utility grid or drawn from the utility grid depending upon the generation as well as demand under distorted as well as unbalanced grid voltages, and to mitigate the power quality issues such as compensation of harmonics, compensation of reactive power, and balancing of utility grid or DG set currents even though it is feeding unbalanced loads, and to ensure the seamless transition from different operating modes without causing any oscillation or overshoot. And coming to the schematic of my developed system, you can see that here a solar PV array, battery energy storage, utility grid, as well as DG set are used as energy sources. Here the PV array is connected directly at the common DC link terminal of the microgrid, whereas battery is connected by using a power electronic interface. And the main advantages of connecting battery using power electronic interface is that we can reduce the voltage rating required for the battery, as well as we can control the charging as well as discharging current. Moreover, during the unbalanced loading in the microgrid, the second harmonics will appear at the DC link. Hence, this bidirectional converter blocks the flow of second harmonics into the battery. Hence, we can enhance the life of the battery. And this DC power is converted into AC power and that is integrated at the point of common coupling where the loads are connected by using a voltage source converter. And here, the three-phase utility grid is connected at the PCC terminals using a solid transfer switch, and that can be controlled to connect as well as disconnect the utility grid into the microgrid according to its availability. Moreover, a DG set also incorporated at the PCC using another solid transfer switch, and that can also control to connect as well as disconnect the DG set into the microgrid according to the system operating condition. And here we are focused to integrate the DG set into the microgrid only under emergency situations such as when the utility grid is not available, where the PV power as well as battery together cannot load demand. Hence, in order to provide uninterrupted power to the loads, we are just integrating the DG set into the microgrid. And moving to various control algorithms that is used in the developed microgrid. And here the one of the challenge involved in the microgrid is the extraction of maximum power from the solar PV array. And there are several MPPT algorithms are available for extracting the maximum power. Here, an incremental conductance algorithm is employed. Another challenge involved in the controlling of voltage source converter. And the main objectives of controlling the voltage source converter are we have to operate the system in grid connected mode or in standalone mode or in DG mode of operation according to the system operating conditions. And then active power injection from DC sources, as well as power quality improvements such as compensation of harmonics, compensation of reactive power to realize sinusoidal and UPF grid currents or DG set currents, and then balancing of the supply currents, even though it is feeding unbalanced loads, then operation of DG set at its maximum fuel efficiency zone when the microgrid is synchronized into the DG set. Moving to the structure of VSC control, we can see this. I have already explained that the system operates basically in three modes: grid connected mode, standalone mode, or in diesel generator mode. First of all, we will check, the controller will check whether utility grid voltage, frequency, and the phase angle are within these ranges or not. If all these three conditions are satisfied, then the controlling signal for the solid transfer switch at the utility grid becomes high, and thereby the grid connected mode control applied to the voltage source converter. And also in grid connected mode, the common disturbance occurs are the unbalance as well as distortion in the utility grid voltages. Hence, in order to improve the quality of grid currents, we need to estimate the positive sequence components of the utility grid voltages. And here an improved second order generalized integrated controller is developed to estimate the positive sequence components of the utility grid voltages. And after getting the positive sequence components, we are estimating the unit templates of the grid voltages for generating the reference currents. Hence, even though utility grid voltages are distorted or unbalanced, we can obtain smooth sinusoidal grid currents by using this improved controller. And moreover, the utility grid the nonlinear loads are connected mainly in the PCC. Hence, the power quality improvements is very essential in the microgrid. If we are not improving the power quality, what will happen? The nonlinear load draw harmonics from the utility grid, and these distorted currents will further react with the utility grid impedance and cause distortion to point of common coupling voltages. Hence, it will disturb all other normal loads that are connected at the same PCC points. Hence, we need to improve the power quality, and here we are estimating the fundamental active weight of the load current, and here the fundamental active weight of the load currents are estimated by using the same SOGI FLL controller, and then the average weight of the load currents are computed. Then it is subtracted with the feed forward weight of the PV array, and that is this component is normally required to enhance the dynamic performance of the system. And then added with the loss component required to regulate the DC link voltage. This component only comes when battery is absent in the system. And this, after getting the amplitude of the utility grid currents, we are just multiplied with unit templates of the grid voltages that is obtained by using this controller. And then reference grid currents are obtained. Then it is compared with actual sensed grid currents, and it is further fed to hysteresis current controllers for generating the VSC switching pulses. If any one of these three conditions are satisfied, that is utility grid is not available in the system, then the controller will check whether PV power is sufficient to meet the load demand, or SOC battery is higher than its lower limit, and it can discharge the power for a longer time. If any one of these two conditions are satisfied, then the controller will detect that system can operate in standalone mode. And here the standalone mode, we are generating reference load voltages of desired magnitude and frequency with minimum distortion. And these reference load voltages are further compared with actual sensed load voltages and PI controllers for generating reference load currents. And further comparison with actual sensed load currents, and the errors are fed to the hysteresis current controller for generating VSC switching pulses in standalone mode. Or when the PV power is lower than the load demand and the utility grid voltages are not available, and then associated battery is also lower than its minimal level, hence it can't possible to meet the load demand for a longer time. If all these three conditions are satisfied, then the microgrid starts synchronizing to the utility grid, and then DG mode control applied to the voltage source converter. In DG mode also, the power quality improvement is very essential, because the power quality improvements in DG connected mode is very significant because the higher impedance of DG set. Due to this higher impedance, the distorted currents react with this impedance and cause more pollution to PCC voltages. Hence, and the power quality improvement is critical in diesel generator mode. Here also we are estimating the fundamental active weight of the load currents using the same controller, and then the average fundamental weight is then further applied to the limiter. This operational limiter is to enhance the performance of DG set to obtain maximum fuel efficiency from the DG set. That is, whenever the DG set draws it 80 to 100% of its rated power, then we can obtain maximum fuel efficiency. And after this amplitude of the DG set currents multiplied with DG set voltages unit templates, we will get reference DG set currents. And then it is further compared with sensed DG set currents, we will get the switching pulses for the voltage source converter in DG mode. And the structure of the bidirectional converter that integrates battery at the common DC link is shown here. And the main function of BDC is to regulate the DC-link voltage. And whenever the daytime, the DC-link voltage is regulated to the MPP voltage of the PV array, hence maximum power can extracted from the system. During the night time, the DC-link voltage is regulated to the minimum value that required for stable operation of the microgrid. Moving to results, and here it shows the operation of microgrid at distorted utility grid voltage. Here we can see that the utility grid voltages are distorted. Hence, the improved SOGI controller estimates the positive sequence components of the utility grid voltages, and that is further used to generate the unit templates of the grid voltages. And then it is used to estimate the reference grid currents. Hence, we can see that sinusoidal balanced and UPF currents are maintained at the utility grid, even though it is feeding power to nonlinear distorted load and under distorted utility grid voltages. And moving to dynamic response in grid connected mode, here the dynamic performance is created by changing solar radiation as well as during the unbalanced load. And we can see that during the change in solar radiation, power fed to the utility grid also changed. And initially, the solar photovoltaic array operates at 1000 watt per meter square radiation. Hence, we can see that the grid currents are 180 degree out of its grid voltages because it is feeding power to the utility grid. And during the reduced solar radiation, we can see that the grid current feeding to the utility grid is reduced. Moreover, from 0.8 second, we can see that grid currents are in phase with grid voltage. That is, generation is lower than demand. And during the unbalanced load also, we can see that the voltage source converter provides the unbalanced load components such that balanced currents are drawn from the utility grid. That is, power quality has been enhanced. And then figures show the seamless transition capability of the microgrid, and figure A shows the seamless transition capability of the microgrid from standalone mode to grid connected mode and vice versa. And here, initially the utility grid voltages are not available, whereas the PV power is sufficient to meet the load demand. Hence, the system operates in standalone mode and it meets the load demand without causing any power intermittency. And at 0.7 second, we can see that grid voltage have appeared. Hence, the synchronization of the microgrid into the utility grid starts. When all the synchronization conditions are satisfied, we can see that grid current flows. And moreover, from 0.8 second, again utility grid voltage have gone. Hence, the controller will detect the change. And here, PV array power is sufficient to meet the load demand. Hence, the control pulse of the solid grid side became lower. Hence, the system operates in standalone mode and it provides power to the connected load. And figure B shows the seamless transition capability of the microgrid from standalone mode to diesel generator mode and vice versa. And here, the utility grid voltage is not available for the entire operation. And moreover, at the starting, PV power is sufficient to meet the load demand. And the system operates in standalone mode and it feeds power to the connected load. And at 0.45 second, we can see that solar radiation has reduced to cause PV power become insufficient to cause load demand. Moreover, SOC of the battery also lower. Hence, the system tries to synchronize to the DG set. And for the meanwhile time, the battery will provide the load demand. And after satisfying all the synchronization conditions, the control pulse of the solid transfer switch at the DG set becomes high, and thereby DG set get synchronized into the microgrid, and then it provides power to the critical loads. Moreover, from 0.7 second, we can see that power again increased to cause it's sufficient to meet the load demand. Then the control pulse for the solid transfer switch become automatically lower to cause the DG set get disconnected from the microgrid, and the standalone mode control applied to the voltage source converter. And moving to conclusion, here a seamless transition capability of the microgrid between utility grid or diesel generators it is presented to satisfy the load requirements without causing any power failure. The PV array is controlled to deliver its peak power, hence the primary priority to meeting the load demand has been given to clean energy source. The conventional diesel-based energy source has been incorporated in the microgrid under the extreme worst operation condition, hence uninterrupted power has been dispatched to the critical loads. Here an improved SOGI controller is developed to improve the quality of utility grid power even under abnormal grid conditions. And the power quality solutions like compensation of reactive power, compensation of harmonics, and balancing of power in three phases are achieved using the SOGI FLL control. And here the seamless transfer among different modes has been realized. Thank you.
Great, thank you very much for your presentation. So it looks like we already have some questions. So the first question is, what is the reason behind using a solid state switch as an isolator or a switch?
Yeah. Actually, we are just sensing the utility grid available or not initially. If utility grid is available, then this solid transfer switch is controlled to connect the utility grid into the microgrid without causing any problem. If it comes, then we again resynchronize the grid into the microgrid by using this switch. Thereby, the importance of switch is coming into picture.
Okay, the next question is hysteresis controller needs fine tuning. Sanjeev, do you have a follow up?
Yeah, sorry. Yeah.
No, that's okay. Go ahead.
Yeah. So what I mean is the switches, because typically the field has a different notion, because they don't use the solid state switch, because when there is a failure in one of the switch, it directly provides a connecting path. So the solid state switches are not used in the field for any microgrid or for any DER connection. But the simplicity of research, yes, we can do it. But the switch, I mean, the PCC switches are completely different than what we generally use. So that's what my point is.
Yeah, correct, sir. Correct.
Yeah. So the other one is actually the hysteresis band, because hysteresis controllers are not not flexible in terms of implementation side, because you may not able to achieve 85% of utilization of your a cap. I mean, I can say like a 0.85 modulation index. You may not able to achieve that.
Yes.
So I don't know how exactly you realize that, and then what is the implementation side of it?
Yeah, actually, hysteresis current control is not used because of its band only. That switching frequency is not in our hand according to the error that frequency decides. So practically, it's not possible to use accurately the hysteresis current controller. But in our laboratory for a prototype, we are using that one.
Oh, okay. Another one is actually like if you just go to the result side. So when you move from a grid connector mode to this one, yeah, I think this one, yeah, exactly. Grid connector to the standalone mode.
Yeah.
How do you actually, if you look at the VSC currents, those are like in grid connector mode sinusoidal, but when it comes to the standalone mode, why they are not sinusoidal?
Actually, in grid connected mode, we can see that the grid currents are out of phase with the grid voltages because we are feeding power to the utility grid. In grid connected mode, battery is having no importance. Thereby, the VSC current is increased because it is feeding power to the grid. In standalone mode, where the battery is coming into picture, because we need to feed the extra generator power into battery. That's why VSC currents is reduced.
Okay, they are reduced, but they are still in the sinusoid.
No. Actually, VSC is controlled to feed the harmonics as well as unbalanced load components. So even though it is in standalone mode, it will provide the harmonics as well as unbalanced as well as real components. So VSC current won't be like sinusoidal.
Yeah, I got it. Yeah. And the other one is the logic side. I mean, the way you implemented from grid connector to standalone mode. Yes, we generally use the basis, but I don't know the way we get it in a laboratory really implies the physical, I mean, the field side of it, because we did not see the smooth transition from grid connector to the standalone mode. So that's what I'm.
Actually, that field implementation is going on in our laboratory prototype, and we got a quite results also while transfer from grid connector as well as standalone or standalone to grid connected mode. But it is in under progress.
Oh, okay. Thank you.
Welcome.
Okay, we've got time for a couple more questions. Any other questions?
If no one is there, then I'll.
Yeah, go ahead, Sanjeev. We still have a couple more, a little bit more time. So go ahead.
Okay. Yeah. Vivek, so I think the switching is good. I mean, the seamless switching and all those things. But how do we really like look at the transfer from the DG dominant? I mean, you have used the diesel generator, and you're saying that we can use 80% of it. But but how exactly, like if you use it for 85% of loading continuously, then what happens over the long time, or the long period of operation? So Did you consider these
Yes,
things?
a good question, sir. Sir, actually in DG mode, we are just operating as like we can say like a constant power, like 80 to 100%, because we realized that when the DG set operates at its 80 to 100% of its rated power, we can achieve maximum fuel efficiency. So nobody will use like in variable power mode for diesel generator mode as like utility grid. Hence, the importance of battery is there is battery also in our system. Hence, even though when the load demand is lower than it's the DG set rated power, we can feed that extra power into the battery. Thereby, we are operating like in a constant power mode. If battery is not there, then we have to make into like a DG power exactly will be equal to load power. Otherwise, instability will cause. Because of battery, we can use it like constant power.
Yeah, but round trip efficiency of the battery is will be still less. It will not give you 100%. Whatever you give it and you will
Correct.
back. So it will
Yes.
again lead to the losses. Then when
Yeah,
you
actually, in that case, we need to consider about SOC battery also. We can't feed the power to the battery continuously. So we need to monitor SOC, because that SOC monitoring real-time implementation is like a hard task. We need to find out some methods to estimate it accurately. So it
Mhm.
is a challenging task process.
Okay. Yeah. Thank you.
Welcome.
Okay, we have one more question. Have you tested short circuit fault in some of your models?
No, actually, circuit fault we didn't realize into hardware system. We are just looking into grid outage in the sense like we are just reducing the grid voltage for achieving that grid outage, or we are completely making grid voltage as zero. So the controller automatically sense the change in grid voltage and automatically shift to the different modes of operation automatically. We didn't focus on short circuit test like.
Okay, one other question. Last question in here is, what connection are you using for sharing load around the multiple inverters and generators?
Sorry, ma'am. Once more. I couldn't.
So how
Yeah.
are you working to share across the different inverters and generators?
No,
For sharing.
actually, we are maintaining load demand as constant, because if we are considering for critical loads, we need to follow the load demand perfectly without causing any disturbance. So that's why the importance of different energy sources in our microgrid comes into picture, and we are focusing first priorities we are giving to the clean renewable energy source such as solar. If solar power is sufficient to meet the load, then we obviously will use that solar to meet the load, and remaining power, if generation become excess, we will get to the utility grid. And then if the demand is higher than PV power, then we will draw from power utility grid to meet the load demand. Hence, and also if all these energy sources are not available, then we are using just like diesel generator to fulfill the load demand. Thereby we are concentrating as our load as like critical loads, such that we have to feed that load demand continuously without causing any interruption.
Okay, well, thank you very much, Vivek. We appreciate your presentation and your Q&A. Thank you for the questions that we've had. If you can put your name and just the title so people have that and they can grab your email if they have further questions that may come up.
Yes.
So
thank you everyone for listening. Thank you.
yeah, thank you very much. So let me do just this, and then I'm going to share my screen. So here we have our last presentation will be by Fosley from West Virginia University. And he has asked me to share his screen. Fosley, I'm going to share it, and then.
Sorry to interrupt, Dr. Schultz. Can I share my own screen?
Oh, sure, possible? You can. You can if you think you're fine. Since you sent it to me, I thought you wanted me to, but go ahead.
Okay, thank you. Can you see my screen?